April 22nd, 2021, a catastrophic engine failure on a 460-foot-long passenger and car ferry near Bainbridge Island, which is near Washington, started a fire that caused more than $3.8 million in damages. On March 14th, 2022, the National Transportation Safety Board concluded its investigation into the incident and tied the fire aboard the Wenatchee to an improperly tightened fastener. A single nut. The fire occurred during a sea trial in Puget Sound after the fastener failure led to components from the engine being ejected and causing a fire in the engine room. Luckily, none of the 13 crew members were injured, and their swift action prevented it from being worse. The issue dates back to November 2020, when the Wenatchee, operated by Washington State Ferries, was taken out of service for maintenance. During maintenance, 2 of the 4 main diesel engines were overhauled by factory-trained technicians. In February 2021, the crew conducted engine tests following the overhauls. Alarms went off in the number 3 main engine, and crew members found pieces of a cigarette lighter in the lube oil system. The maintenance technicians came back, drained the oil, and searched the lube oil system for 2 days. They recovered about 70% of the cigarette lighter's plastic and metal components and told Washington State Ferries that it was fine to run the engine. However, none of the engines were run again until the vessel headed for a sea trial. In April, during the post-maintenance sea trial, the connecting rod assembly in the number 3 main engine failed and ejected components that breached the crankcase and ignited hot pressurized gases. The crew contained the fire by stopping all fuel supply and ventilation to the engine room and isolating the space. One crew member witnessed, quote, "fire, smoke, and debris flying everywhere." Engineers examined the lube oil system to see if the cigarette lighter could have caused the engine failure. While they found parts of the lighter throughout the system, they found nothing that would suggest the lighter parts started the fire. The NTSB found that the probable cause of the mechanical failure was the connecting rod assembly that came loose due to insufficient tightening or torquing of a lower basket bolt during the previous engine overhaul. The NTSB stressed that maintenance technicians should use a calibrated torque wrench in compliance with the manufacturer's recommendations and verify that all required torque requirements had been completed. This is not the first time that improperly torqued fasteners have caused problems. A fire aboard the Carnival Liberty cruise ship in 2015, a fire on the Nanita bulk carrier in 2016, and an engine failure on the Red Dawn offshore supply vessel in 2017 were all traced back to bad fastening, according to the NTSB. The Wenatchee was built in 1998 and can carry up to 202 vehicles and some 1,800 passengers, so it could have been much worse. All because of a, quote, engine assembly error, or nut that just hadn't been torqued right. The operator cooperated with the investigation, provided recommendations to prevent future incidents, and is designing and installing a video camera system with fire and smoke sensors for the Wenatchee and other vessels in its class. I'm David Manti. Tighten those nuts.
Wow, $3.8 million from just one fastener that had failed. So you're looking at a possible few dollars maybe for that fastener, maybe less than $1. And if it's not done and properly torqued, you can see the amount of damage that can be done from the fastening process. So thanks very much for joining us. I hope you found that story a little bit illuminating about the number of failures that you may see within a certain industry or in certain segments where there is quite a bit of safety critical issues dealing with torque and the components that can fail and cause a tremendous amount of damage if those fasteners aren't torqued correctly. So just to say hello, my name is David Cash. I'm a member of the marketing team here at Mountz. I'm glad that you've joined us for today's presentation. I hope you find it interesting and that you can gain some knowledge and better help in your applications as it relates to applying torque. So we look at our topic today, and we're looking at 3 different ways that we can prevent over torque failures with the CamOver Wrench technology. So let's go ahead and jump right in. And we looked at this particular story and highlighted it, and the human component within the manufacturing process is probably the biggest contributor to possible fastening quality risks that are available. Is the operator completely trained in that? And we'll touch base on that here in just a moment as well. So the human element to the manufacturing process is really a very big component to the formula for getting a good quality fastening process. Next, over-tightening is another component that can really affect the outcome of a part that may be failing after the item has left or been delivered to the customer or end user. And along with that over-tightening process, it can really put a fastener into its yield point, and once it goes past that yield point, any type of vibration or any type of shock to that can cause that fastener to break. And so we have fastener breakage that can happen, that can really, again, lead to quality risks that we can try to avoid. And basically what that looks like is every fastener has a certain tensile load that it can withstand. And if we get to an area where the fastener has been stretched to where it starts to become plastic after it moves from the elastic region, meaning that the fastener will be allowed to return to its normal state after the load has been removed. But in this case, once we get to the yield point and just past that, we start to see deformation in the tensile load on the fastener itself. Now, in this example, this is not a fastener, but if this was threaded, then we could certainly use that. But at some point, that fastener gets to its yield point and it will eventually break over load. And so this is what happens when a fastener is over torqued. It can be put into that region where, again, a simple shock, vibration, other types of inputs can cause that fastener to break, and that you may see much later after a component has been delivered. And so if we look at this graphically, this is what we see. Our peak point is going to be the yield point, where the fastener will move from the elastic region into the plastic region. Now the yield point is going to be a little bit lower than where the fastener will totally fail. However, in that area, you could see that it's not too much more amount of force that would be needed to go ahead and cause that fastener to break. So typically, when you look at the tensile strength of fasteners, there's a proof load number that is given, which is usually 85 to 95% of the yield point. And then torque values can be in that general area as well. They could be about 75% of the proof load, or up to 85% of the proof load. It just depends on the application and the amount of clamp force that you may be looking for to get. But the over-tightening process can really cause a lot of failures within the manufacturing process. Some of the other manufacturing risks when you do get failures, obviously you may get a lot of scrap. And so any type of parts that can no longer be used because of a failure, you're going to accumulate additional expense in dealing with those particular scrap rates. And then finally, you're looking at the ability to have an error proofing process in there. And so if you don't have that type of process within the fastening, anything that you can use to help eliminate any type of possible error. So if we can basically deter or head off or make sure that the operator cannot cause a mistake, then we are in that area where we're helping to error-proof that particular assembly or process. And then we want to make sure we've got the right tool for the right application. And so with all of that, that kind of all falls under our torque control goals. And if we have really good and proper torque control, then a lot of those risks are really well mitigated. So if we have the correct tool, the correct process, if we're applying the amount of torque, if we can ensure that the process is good and reliable, that it's efficient, and that we're getting uniform conformity or consistency within those particular applications. And again, we can help to reduce the scrap rates and other components that would go into actual items that would deter from the costs of that particular application or process. And so when the quality is at risk, we want to make sure that where the application itself is up to 100% foolproof, that we can use a specific tool or item or process that can help us get to that point. And if that is good, then we can really help to, again, increase our quality, increase our throughput, and make sure that everything is happening in the way we like it to with that particular application. And so when we look at the three ways that we can improve the process control and help to prevent over torque events, first is going to be the operator influence. If we can eliminate the operator influence in the tightening process, then we can really help again to make sure that we're getting all the torque that we are needed. We're not adding additional torque, or the operator is not influencing what the outcome can be. Again, the operator plays an important part in the fastening process. And if they are, again, properly trained, if they understand what is happening with the tool that they're using, the more understanding they have within the application, it can really help to educate them and to give them a sense of understanding what power or what control they can use to influence what's happening with that assembly process. And so the operator influence, if we can help to eliminate that, that is certainly going to be a bonus. If we have the proper tool selection for them, so if there is a tool that we can use that can also help to eliminate any influence that they have, that's going to certainly be a big plus with that operation. If there is the way that we can implement an error proofing tool within that process, again, we can really help to make sure that no matter which operator is doing a particular fastening, all of the outcomes are going to be the same. And then we could also use a preset tool to help with the process of the reliability for that application. And that's our second point, is being able to use a preset style of tool in an application where the operator does not have the ability to change a torque value. You can tell a preset tool has no scale on it. It is adjusted and set internally. So again, the operator has no way of accidentally changing the torque that they're using. with an assembly process. So if we can eliminate the operator's influence, if we could use a preset style of tool, those are the first two items within the actual process. And then the third one is going to be the actual torque wrench mechanism that's being used for that specific style of tool. And so there are a number of different torque wrenches, and all torque wrenches apply torque, but not all torque wrenches apply torque the same way. And being able to understand how a particular style of torque wrench applies torque can really help you to evaluate a certain application and decide which tool is going to be the best for that specific application. So if we look at the click wrench, it is by far the most popular and most used wrench around the world. They are very inexpensive, which is a plus, and they do deliver torque accurately within the use of the tool. However, this style of tool is greatly influenced by the operator. And when you use a click wrench, there is basically only 3 degrees of deflection from when that wrench clicks until the operator is adding additional torque to the fastening process. So if you see an operator that pulls the wrench really fast, that is going to be adding additional torque to the fastener. If you see operators that will double click or triple click, you will be adding additional torque to that fastener for sure. However, if you see an operator that is very deliberate with how they pull on the wrench, they're going very slowly. Once the wrench clicks, then they release the actual wrench itself and not apply any torque. Then the click wrench can be very accurate. But again, it just depends on the operator and who is using it. It is very much like driving a car and you need to stop at a stop sign. If you are going really fast and trying to stop behind the line, you may overshoot that because you were going too fast. However, if you're going the proper speed and you slow down appropriately, you can certainly get a more accurate stopping distance from the stop sign. So that is kind of the thought behind the use of the click wrench. Again, if the operators on Monday may not have had a great weekend, those wrenches may be, the frustrations may be taken out on the use of the wrenches. And so, again, it just depends on who's using it, how they're using it, and if they're using it correctly, if the click wrench is going to give the results that that would be needed and required for a specific application. And if it's a really safety critical application, then the click wrench may not be the best tool for that particular application. So next, the next style of mechanism is going to be the breakover style of wrench. And so with the click wrench, we saw that it normally takes about, or it is about 3 degrees before the wrench starts adding additional torque. If we look at the breakover style tool, we can go anywhere from 20 degrees to 90 degrees of break with that particular tool before you start adding additional torque. And so this wrench really helps to give you the torque signal at a much greater ability to stop pulling on the wrench once the torque has been achieved. And we'll take a look at these styles of wrenches when we go to the demo portion of the presentation as well, to give you a little bit better idea of how these work. But again, these are set internally, there's no way for the operator to change the torque value. So if when that wrench breaks over, the torque has been achieved, and then the operator can move along in the assembly. So the breakover wrench gives us a much greater control than it would be with the click wrench. And then the next is going to be the CamOver style of wrench. And so with this particular mechanism, this allows the operator to fully provide 100% of the torque from the tool to the application without any chance of over torquing the fastener. Once the torque has been hit, the cam inside the head of the tool will simply rotate and slip, and now there is no torque on the application or on the fastener. And once, again, if the operator tries to come back and wants to do a double click, so to speak, on that, they can never go past the cam point of the wrench. So there's no way that they can add any additional over torque to the application. And so these tools, again, are set internally. They allow the operator to hold the tool anywhere up and down the handle. There is, because our fulcrum point is at the end of the tool, there makes no difference on where the hand is being held on this particular tool. Obviously, we would want to hold it on the handle and use it there, but if you change your hand position on a click wrench style, because the fulcrum point is on the inside of the wrench, you are changing the torque output formula. And so if you're going closer to it, you're adding more torque. If you're going away, you're losing torque. Again, the CamOver style of a wrench gives you 100% torque control on that application, and it's a non-length dependent style of tool, and it doesn't matter which operator would use the tool, you're always going to get the torque output that you're looking for with the CamOver wrench. And so we looked at some of the accuracies of the wrenches. We've kind of touched on them, but the click wrench, again, is basically a signal type of wrench that's very limited. Once the wrench clicks, that's it. So it's letting you know that you've hit your value and stop pulling. But if you don't, you obviously you don't prevent the operator from adding additional torque. And again, if it's being used in a safety critical type of application, it can really put the accuracy at risk by the use of that style of tool. The breakover wrench, again, is also a signaling type of wrench. However, you have a much greater expanded visual indication of when you've hit your torque value. So you can stop pulling on the wrench, so you don't add any additional over torque. So it really helps to reduce the risk with a real clear signal of when the torque has been achieved. And then the CamOver style of wrench removes the operator influence altogether from the actual torque delivery. It helps to error-proof the torque delivery, and you get precise and accurate torque with the use of this style of tool. And so with all of that, there is one other style of wrench that is being used, and that's going to be the digital style torque wrench. Again, this basically would act very similar to a click wrench, that the wrench itself is going to alert you when you've hit a certain target. However, it does not prevent you from adding additional over torque to that fastener if you don't stop pulling in time after the signal has been given. So that is a lot of what the different mechanism styles can do in a fastening application and when torque is being applied. So at this point, let's go ahead and take our poll question. So in your facility, are you using click wrenches, breakover wrenches, cam, digital, or a mix of different types? So let's go ahead and take that, and we will see what we end up with here after our answers have been gathered. All right, so the majority is a mixed type of wrenches, followed next by click style wrenches, and then digital and CamOver and Breakover are near the bottom of the poll. So thanks very much for participating with that. So let's go ahead and we can jump into our demo portion where we can look at the different wrenches and show you a little bit more about how those function, and you can actually see those tools in action. And so with our setup here, I've got all of the different wrenches that we've talked about, except for the digital wrench. But I've got a click wrench here. We've got several different breakover style tools, and then we also have a CamOver style tool as well. So if we go ahead and let's see here, let's move this here and slide that guy. All right, so when we look at the click wrench itself, to give you an idea of how that tool functions and what you see when the wrench actually clicks, then let's go ahead and show you the components within the actual wrench itself. And so I have this click wrench here, and what I've done is I've removed the little pin that holds the head on. This head is basically where our fulcrum point is here, where the that pin locator is, and then inside there we have our spring mechanism, which is what we're compressing to provide the torque value that we are trying to achieve. And with that, we have our follower and what's called the jump block. So let me go ahead and just zoom in a little bit here so you might be able to see this a little bit better. All right, and so the way that this this simply works is the jump block here is in between the follower and the actual block itself. And as the spring compression pushes up on the mechanism as the wrench is being pulled, the actual block will just simply slip, and it kind of just clicks over, and this head here is what you hear hitting the inside of the wrench when the jump block, in this case, rotates from its flat position, and then it will jump and rock over, basically giving in to the pressure that's being generated or pushed on it by the spring mechanism. So to kind of show this in this direction, we would have our block and the follower here. And when the actual wrench inside or the jump block will pivot, this clicks on the inside of the tool, and that's where you get the actual click that happens within this style of tool. Now there are a couple different other styles of click wrench that use a different mechanism, but this is primarily the style of click wrench that you will see in most wrenches today. So that is how the click wrench works. Now, if we want to go ahead and we can put our torque tester here, and we can show you how the actual torque is achieved with the click wrench, and how easy it is to be able to add or give it the over torque within the actual torque delivery. So let me turn this down so you might be able to see it a little bit better. All right. So, okay. So the wrench itself, we can set our mode in here for our testing. And what we're going to do is move it to first peak. And what this does is it actually captures the point at which the wrench will click. So, and then it will also show us if there was any additional over torque. Now, if I pull this wrench very deliberately and slowly, let me move this back out so you can see what's happening. There we go. So you can see that I clicked the wrench at right around 10 inch-pounds or so, but our final torque value was 15. So if I clear that and I pull it with a deliberate amount, or being very cautious of what I'm doing, you can see that again we're at 10 inch-pounds or so, and I've got the same exact value for the final torque. But if I was to double click this, you can see again we're clicking right around 10 inch-pounds, but I've added 20 inch-pounds of additional or the final torque with that just by doing the double click. And if you get an operator that goes very fast, again, you can overshoot your target and add, in this case, almost 15 inch-pounds or the final torque there. So the click wrench, again, is a very operator influenced style of tool. And it may be really good for a number of applications, but again, in really critical applications where over torque is something that cannot happen, the click wrench would not be the best tool to be able to use in that situation. Next is going to be the breakover style of tool. And so when we look at the different kinds of breakover tools, this particular tool is an open-end head that you can use here. You can put a number of different styles of heads on there, boxed end heads, you could put a ratcheting head, or you could put an Allen key on there, and you can also make them interchangeable as well by using a different interchangeable head where you can pop this onto the tool and change that. But how this tool works is, again, as you're applying torque, once the wrench begins to break, then you've hit your torque. It will go all the way past 90 degrees, but that's really not necessary to do that. Once the wrench begins to break, you've hit your torque value, and you're no longer adding any additional torque from the 20 to 90 degrees within that. So there are a number of, again, different ranges and styles that you can use, from lower torque values up to a much higher torque value. And again, once the wrench begins to break, you've hit your torque value. And so if we want to test this type of tool, we can do very similar in the testing. But once the wrench begins to click, then you're going to hit your torque value. So let's go ahead and put this into peak mode. And what we'll see is the highest peak torque generated. And so we're at right around 20 once this begins to break. And so again, you don't have to pull it all the way until it breaks over all the way. But once you see it begin to break, then you've hit your torque value. And again, you're not adding any additional over torque. So this is also a very good style of tool for safety critical applications, that where you can watch and see the tool visually break, or if you want to get it to the breakover, full breakover style of position. Again, these are set up, and the torque is changed by using the internal components in there, and I can show you what that would look like. But this is our CamOver style of tool. Again, this wrench is simply going to slip once we've hit our torque value, and we can go ahead and show that here on the analyzer. And so I think this one's set to, right around 33, 34 inch-pounds. And so you can go ahead and cam that tool over, and it's never going to add any additional over torque to the application. So it really is the best tool for getting accurate and consistent torque delivery on the fastener. If we want to change the torque in this, or we want to set it to a different value, there is an end cap here that is removed. And then inside is the adjustment mechanism. You might be able to see it in there right about there. But an Allen key comes into the tool, and then we can turn it up or turn it down to add or loosen the desired torque that we want. So now we're going a little bit higher in torque than we were at our 34 inch-pounds. So that is the CamOver style tool. And again, these can go from a lower torque all the way up to about 90 or so foot-pounds with the CamOver style tool, which is going to be, again, by far the best choice for any safety critical or any type of applications where you may be seeing really inconsistent torque values because of the torque wrench mechanism that's being used with that tool. And so with that, let's go ahead and move to our question and answers. Chris, do we have any questions?
Morning, Dave. Yeah, we had a couple questions that came in. First one is, on the grabbing of the handle, why does the length dependency depend on impact the tool and its torque value?
So again, if we look at the click wrench, for example, our fulcrum point is right here where this pin is, and so this is calculated with this offset being used with the end of this tool. So the tool is designed to be used at this ring in the handle, and so if we change that length in here, we're now changing the output that is being, or the offset that is calculated from this point to this point. It's a little bit easier maybe to see it on the Breakover wrench, where our fulcrum point is here, and we have a line designated on the end of the tool where the operator would use the tool, and all of the different heads are that are used are calibrated with this offset in mind to be used at this point is where we'll get the actual torque that we want to get. If we change the where we hold it, then that's going to affect again the formula for calculating torque with an offset. With that, with the CamOver style tool, our fulcrum point is right at the end, so it's never going to be. It will never change the torque output because our force times our distance is always going to be the same because we don't have an offset that we are taking into account as we would with a click style wrench or even the breakover style wrench.
All right, thanks, Dave. Next question we have is, how often do you calibrate the torque tester?
So the torque tester can be calibrated every 6 months. It could be every 12 months. We have some customers that will request a calibration cycle at 18 months. We would recommend it be done every 6 months, but a number of companies that we service and deal with have their calibration set to 12 months.
All right, thanks, Dave. Next question, on the preset tool, does it require a torque tester to change the torque value?
So it would require a torque tester to validate to make sure that the wrench is being set to where you need the torque output to be. So yes.
Okay, thanks, Dave. Next question, can you use a CamOver wrench for any size screw?
You certainly could use a CamOver style tool for whatever the torque range would be for that particular fastener. So as long as the range of the tool is going to correspond to the torque output that's needed, you can certainly use an adapter to the 1/4 inch square drive or 3/8 or 1/2 inch, depending on what your particular output might be or needed for the input of the fastener.
All right, thanks, Dave. Next question is, how often do the wrenches need to be calibrated?
So these wrenches fall under the ISO 6789 calibration standard, and that standard is every 5,000 cycles they should be recalibrated.
All right, Dave, thanks. That looks like it's the last of our questions.
All right. I want to say thank you very much for joining us today. Again, if you have any questions about any of the styles of wrenches, or you need some more information, feel free to reach out to us. We can contact our technical application team through our website, or we can have a sales representative talk to you about your specific needs. So thanks so much again for joining us, and we'll see you next month.